Yeah, we can start now. So, like once again, like, could you able to hear me now properly? My voice is clear,
Yes,
right?
clear.
Okay. So, all right, thanks. So, we can start. We are already on time. So this is your week 4, and so in week 4 you have seen some lectures on nuclear magnetic resonances and something more about like some time dependent Hamiltonian systems. So like right in that context, you have questions in the I mean in the I mean for this week's assignments. So and I hope like people are going through those assignments and also lecture videos and also like it's been week 4, so you need to run through well. I mean because there are I mean this is halfway through this course. You are already and then there are 4 more weeks and then you will conclude it. So and nuclear resonance like which has been going recently, like that is one of the important topics, and many applications like you have and many important research works like uh, like is in this topic. So I hope like this is something you'll find interesting uh, and also you understand them well. So yeah, so we'll talk about time-dependent Hamiltonians and some problems. Mostly, we'll try to understand things from various problems. So moving on. Last week, like as we like, I mean, as we ended our session, like we also wanted to discuss some more couple of problems, which is something quite related to the uh, time dependent Hamiltonian. So I was about to discuss about that, but like unfortunately we don't have time anymore last time around. So we'll revisit that. So this is something also quite relates to this week's uh, problem. So we'll see how and uh, yeah. So like last time as we were talking about some angular momentum and spin algebra, all these stuffs. So you probably have some a good amount of idea or some. Uh, I mean, in the context of spin algebra, you at least have some fair idea like how you solve those. I mean, particularly like determining probabilities and some expectation values. So working out with spin of quantum mechanics, right? So that is what something we need like quite significantly in the upcoming topics. So here as well, like you can see, like we are talking about this problem where an electron is at rest in an oscillating magnetic field. So when that magnetic field is given uh, by this B not cos omega t. So this is an oscillatory magnetic field. So it's like an electron is at rest, and with in the electron, I mean, a magnetic field, oscillating magnetic field is imparted or is given. I mean, in the location where electron is like residing. So so you will see like and that the magnetic field was applied along the uh, uh, z-axis of uh, along the z-axis. So and you know very well like electron is a spin-off particle. It has a spin angular momentum, and its spin angular momentum I hope you have seen from previous idea or know this that fact of Lamar precision or the spin basically tries to align with I mean angular moment the around the magnetic field. So the precision of spin. So that is a different topic. Like I was just telling that like that is something you see a spin-off particle in presence of a magnetic field. So like the magnetic field is applied along the z-axis. So you and we also know like spin-off of of a particle along the z-axis, what is the spin, how spin behaves, and I'm talking about like the spin eigenstates and all these things. So that is what something we would look through. So like calculate the Hamiltonian. So first task is to calculate the Hamiltonian. So okay, so let's see. Uh, the Hamiltonian is uh, like if a like uh, um, yeah. So I hope like you know something about this. Like when a uh, um, magnetic like a charged particle in is kept in the magnetic field, so that the charged particle will have some like this magnetic potential energy. So in that similar idea, I mean, from that idea, like like we will call the energy of that spin-off particle, which is there inside this oscillating magnetic field, will be the Hamiltonian. So that I am writing as minus gamma b dot s. So this is something like you will get it like you have seen this from your electrodynamics courses or previous uh, course, that like you have some idea that like if a charged particle is kept uh, like inside a magnetic field, like I mean you experience some magnetic potential that is m dot p. So so from here only, like you from this m is that magnetic dipole moment, which like from here you basically get this uh, uh, I mean, I'm talking about the spin. Like you will, like after solving this, you will extract out spin gamma. Like this gamma is something related with this power magnetism, and so yeah. So so this is the Hamiltonian. We will see like from this from the given magnetic field, like what would be the explicit form of Hamiltonian. So the magnetic field is given to be something B naught cos omega t, and the Hamiltonian is yeah, and the P naught cos omega t, that is given along the z, that is k. Yeah. So magnetic field also you have this along kk, and then here you will have sz kk. uh, I mean, you have you. It is not really like specified to you, like along where the spin of that electron is pointing. It can be in any arbitrary direction. So if I would write like this form as well, xx, I I hope this is the right way to do it, because if you write the SZ, so I'm like specifying like like right before like I mean computing the exact Hamilton. Like if I write just SZ or simply only SZ, or even this full like after all the Hamiltonian is going to be the same, because the magnetic field is applied only along the one direction, that is Z. So then if I see this, then this would be SZ. So and SZ, we know like we've been talking about SZ like since last week. Like we said like uh, we have for spin-off particles we can construct three matrices S, X, X, Y, and Z, which are something like given by like SZ is given by something X bar by 2, 1 0 0 minus 1. So using that, like, we have Hamilton minus down b naught cos omega t, and we also have h bar. So we can put h bar here, h bar over 2 1 0 0 minus 1. So yeah, so this will be our Hamilton. So is it fine? Like, this will be the Hamilton. So did you get right? Or do you have any problem? You can speak.
It's okay.
Okay. Uh, well, the next we have, if the electron like initially like is spin off state with respect to x-axis, that is uh, that is how it is denoted as determine chi of t. So it is telling us that like as we said, like initially we don't know like what is the spin orientation of the electron. So I mean it can be in any arbitrary spin, like for that, like which we like assigned it to be something sxi, xy, z, and xj k, because it can be in any arbitrary direction. And now, like suppose if it is an if it is given in x direction, if the initial speed is in the x direction, so and the state corresponding to the x direction would be something upstate. So we know, like for each spin there are for each spin direction there are like two eigenstates. Like for sz also we have seen like previously, like we have upstate and downstate, and similarly for sx also you will have two states, and for sy. So uh, so like for SX again, recalling last time what we were doing, like we like talk about this SX, as we have seen right here, SZ can be written in form of a matrix. Same way we can also write SX and XY, which we have seen that in last week's discussion. So like if you remember, like we wrote SX something like this, and its eigenstats, or basically its eigenvector, was something like uh, estimated as like I mean its eigenvalue of Sx. We will have two eigenvalues, like one would be one was this, and the other was one minus one. So these were two eigenvalues. So in our second problem, it is given that the spin of state was initially found. Uh, so this is for the Sx spin. So we are looking at the x component of the spin, which is whose eigenvalue are given by this. Let's say this is upstate and this is downstate. This is how we call it, and the initial spin is given to be this. So this is our initial state of the electron, and if this is the electron's initial state, then we have to calculate what will be its state, uh, determine chi of t. So we are given chi of 0. So chi of 0, that is 1 by root 2, 1, 1. Then we need to calculate chi of t. So we will call this chi of t to something a of t and b of t. Like we'll see that, like we have to determine this chi of t. So where a of 0 is equals to b of 0 equals to 1 by root 2. So that is given to us. So that is the initial state of the electron. Now if I have to calculate this chi of t, then I have to start from the Schrodinger equation. So from Schrodinger equation, I know this del chi of t, del t equals to IH bar chi of t. So that means I can write, uh, sorry, this is, yeah, this is Hamiltonian. So, uh, uh, yeah, so if I take the derivative of chi of t, so that will give me, or let me write this a bit more precisely. So our h is given to be h, as we found out, it is this minus gamma b naught minus gamma b naught h bar over 2 cos omega t 1 0 0 minus 1, and then chi of t, yeah, and this chi of t is a column vector which is a of t b of t. So if you solve this, you will have minus gamma b naught h bar over 2 uh, cos of omega t a of t and minus b of t. So then, right, then I have IH bar A dot and B dot. So this A dot B dot represents derivatives with respect to time. Minus gamma B dot H bar by 2 cos of cos omega t of t and minus B of t. So that, okay, then we can write further. Then yeah, then you have to equate LHS and RHS. That forms your, that will give you two differential equations, one in N, other in P. So that you can write. So let me write for the A. So it would be A dot equals to, if I take I and H bar will go with, there are H bar on LHS and RHS, so you can cancel them out, and so you have I, and that is I gamma b naught by 2 cos of omega t a. So you solve this differential equation. So this is your, like, your first differential equation, and same way you will have another differential equation where you will have this expression b naught I, this will be minus I gamma b naught by 2 cos omega t b. This is the second differential equation. So, like, solving one will give you, uh, yeah, if you solve the first differential equation, this will be, this can be done like this. I gamma b naught by 2 cos omega t dt. You integrate them out. So, and if you integrate it, so you get something, and also the initial condition is given to us. So uh, a of 0 is 1 by root 2. Yeah, so if you solve this, you will have log of a, then log of a, then I gamma b naught by 2. This is sine omega t over omega some constant, let's say that is k, and yeah, and that this a is basically uh, k, sorry, k exponential of uh, I gamma b naught by 2 omega sine omega t, and so we know this initial condition. So if you put this, then you get k to be like you get k to be 1 by root 2. So and because here a of 0 is k, so k is 1 by root 2. So the final form of a will be 1 by root 2 e to the power I gamma b naught over 2 omega sine omega t. Right. So that is your a, and same way you can get what is b. So like b also, like you will get something 1 by root 2 uh, minus I gamma b naught over 2 omega sine omega t. So so finally you will have chi of t as 1 over 2 exponential I gamma b naught over 2 omega sine omega t, then minus yeah, this is minus I gamma yeah, minus I gamma b naught over 2 omega sine omega t. So that is your chi of t after time t. So initially it was in the eigenstate of Sx, that is spin along the that is the x component of spin. So so that eigenstate will change into this state after time t. So like I mean, so yeah, right. So initially you had chi of 0, uh, now it went to chi of t. So chi of t is now this, and chi of 0 initially you had 1 by root 2 yeah, 1 1. So this is the transition you will see after time t. So uh, is this clear to you or any problem?
It's okay.
Okay, fine. So yeah, then yeah, we have to calculate the probability. That is the next co- question is about. So you have to calculate the probability of getting minus h over 2. So minus h over 2, that is when x is measured. So that means you are getting, so when you are measuring sx, you would supposed to get the downstate corresponding to the sx operator, that is the x component of spin. So uh, what is the probability of getting that state after time t? Uh, yeah, we can start it. So okay, uh, so we have chi of t as 1 over root 2 exponential iota this this odd vector is there, sine omega t, sine omega t. Now, like, uh, what is the what is the probability that uh, this is basically uh, sorry, what was exactly after time t? Yeah, what after time t? Okay. Now, after time t, like, what is the probability that this should be like equals to? I mean, so so this corresponds to minus h bar by 2 uh, eigenvalue for Sx equals to 0. So, yeah. So we need to see. I mean, uh, this 1 by root 2 1 minus 1, it, like, uh, possibly the state after when you measure this chi of t after time t. So that means when you yeah. So again, for estimating probabilities we take inner products. So you can take inner product between this and this. So that like, can let me call this something else, like, uh, like we were calling, yeah. So let me call this as chi minus x. This is chi minus of x. So that means uh, probability uh, chi minus x. This is chi mod square. So that is how you take probability. You take the inner product. So this is the inner product. Then you, after taking the inner product, you take the absolute square of that inner product. So that is the, this is the probability. So that means so chi minus x chi inner product. So this is inner product means I have to put a table because I have to take for inner product, like we already have the states in form of matrices. So when you take inner product, so you take, so let's say you're taking inner product of two matrices A B, so that is given as A dagger B. So now we are taking inner product of chi minus x with chi of t. That means we will take the we will take the dagger of chi minus x and do the matrix multiplication with chi of t. So that means do 1 by root 2, 1 minus 1, 1 by root 2, then the entire thing. So this is gamma b naught, gamma b naught over 2 over sine omega t, gamma b naught over 2 omega sine omega t. Then, yeah, then that is 1 over 2. Uh, I gamma b naught over 2 omega sine omega t minus psi gamma b naught over 2 omega sine omega t. So yeah, then this is this entire expression becomes like, you will use the Euler's identity here. So I hope you are aware of that Euler's identity. So we can write like the trigonometry expressions, like I'm talking about like cosines and sine in terms of exponents. So this is like I hope you are aware of this. This is the form for sine, and for cos you know this. So now, using the earlier form, so I have sine gamma to omega sine sorry, yeah, sine t. So this is what you get, and then I have to take for probability. I have to take its mod square. So that is to sine omega t. So this will simply give you this sine square gamma v naught to omega sine omega t. So yeah, okay. So I hope like you do get this uh, the way to calculate this probability.
Yes.
Okay, so then at last we have to this we have to see what is the minimum magnetic field required to force a complete flip in SX. So uh, that is what it is telling us, that the probability that which we uh, like uh, got here. So I mean, uh, like this telling what is the minimum magnetic field required to force a complete flip in SX. So complete flip in SX, that means like if we are in I mean like in the upstate, like initially it was in the spin upstate. So then what is the probability that uh, it will completely go to spin downstate after this time t? So that means that your probability is high. I mean, like your probability is high means like uh, your state is completely going to. I mean, what I'm telling. So initially you had this is number 4. So initially you have spin up, and now you are going to spin down after t. So this means complete flip, because it is initially up, and now after time t it is going down. Or if it is in down initially, then it will go to up after time t. That is complete flip. So if it would have been gone to something like this after t, then like some kind of linear combination C1 up to C2 down, then that won't be a complete flip, because though it has downstate, but still it is mixed with somewhat upstate. So that is what not asked here. So uh, for this complete flip, that means the probability is completely 1. I mean, probability of getting this down state is 1, because you don't have any mixture of up and down. Like you will say that if it would have been something, if like as I was like yeah, earlier as I was telling right now, that if it would have been something, some combination of this, then probability of getting this down state like would be something like would have been less than 1. because and other uh, half will go to this upstream. The probability will be distributed in that way. But now, since in the in your final state after time t, you have downstate, which is completely flipping. That means your probability is maximum that it will, with complete certainty, it will flip down after time t. So that means your probability is one. Uh, then from probability expression we know that p is given. So this is probability. Probability. Uh, so so from the probability expression which we got, we have to basically equate sine of p with 1. So from here, uh, so we know like this is sine square, and for sine square we know like at pi by 2 values, the value of sine is maximum. So that means we can say that argument part, the argument of this sine square is basically is pi by 2. Only then you can have this sine square expression to give you one, which is your maximum probability. So this is pi by 2. And so yeah, so from here like you get uh, b naught pi omega gamma sine omega t. So okay, so yeah, this is fine. You get me?
Yes. Yes.
Okay. So yeah, that was for this part of the question. Yeah. So then, okay, then go to the next question. So now, like what we have the same spin-off particle, like the electron, for example, what we were doing uh, in the time-dependent magnetic field. So now the magnetic field is this. This is the magnetic field. So earlier we just the initial magnetic field, I mean the magnetic field which was given to that spin-off particle electron was along this only what I mean the z direction. Now we have this magnetic field. So now in this magnetic field, like this is a more general magnetic field which is time dependent. Along with it is like could be in any arbitrary like or direction. So like you have both, I mean all the x y z components. So now we will be doing the similar exercise here as well. So we'll start like looking into what is its Hamiltonian, and then we'll look into the other things. So like, like beginning from Hamiltonian. So first we have to like calculate the Hamiltonian as we did before. So yeah, so like as I was telling, the Hamiltonian can be written as something as some. magnetic potential energy. So that is mu is magnetic moment. Mu is magnetic moment. So yeah, and minus gamma s dot b, and s you can like we will write again. S can be any arbitrary, so we'll write sx I s y z plus s z k dotted with the magnetic field expression which is given uh, u dot sin theta cos omega t I plus b dot sin theta sin omega t z and plus b cos theta k, right. Then then like again uh, use the like sx form. So like as I uh, showed you before, like this sx can be written in this matrix forms where this is sigma x, where xy is h bar by 2 sigma y, and sz is h bar by 2 sigma z. But sigma x, sigma y, sigma z, like they are the Pauli matrices. So sigma y, sigma x, Pauli matrices, and sigma Z, like these are like as I showed you last time also, like these are Pauli matrices, sigma x is 0, 1, 1, 0. So like that we have. So so we have talked about this matrices and we have used them like like many times. Uh, then yeah, so if you use this form, uh, you will have minus uh, gamma, then d naught, that is the common factor among all, so that is minus gamma d naught. Also you have h bar over 2, so then you will have, yeah, d naught sin theta cos omega t sigma x plus d naught sin theta sin omega t sigma y, then d naught cos theta sigma z. Yeah, then that is your minus gamma b naught h bar over 2. So if you use the matrix forms, which like uh, so like you have to use the matrix form uh, sigma y. Let me write sigma y as well. So that is sigma y is 0 I 0. So then that will be uh, yeah. Here b naught I have already taken the common outside. So I have 0 sine theta cos omega t. Then I can have sine theta cos omega t 0. So this is your first term, and same way you have 0 I sine theta sine omega t I sine theta sine omega t 0, and then further you have cos theta 0, 0 minus cos theta So yeah, then that is basically if you write the complete uh, matrix, then that will give you cos theta, the first entry, and then you have sine theta, uh, sine theta, you have cos omega t plus I sine omega t, then you have minus cos theta here. Here you have sine theta, uh, sine theta, right. Again, you have cos omega t plus I sine omega t. I think there was a mistake earlier in defining the volume matrices. Yeah, so there will be a minus sign here, which I missed it. So, so there will be minus sign here, and so this is your minus sign. So yeah, sorry for that. So right, then you see again from Euler's relation, like what we were talking before. So this again you can you can write it in exponential. So then finally you can write the Hamiltonian, which is time dependent, as minus gamma b naught s power 2 cos of theta uh, minus I omega t sin theta e I omega t sin theta minus cos theta. So that is your Hamiltonian. So okay. So is this clear or any doubt?
No, it's okay. Clear.
Like anything like I mean, not following you can immediately like you can ask. So there is no need to wait for any moment. So you can drop your query like, whenever you are having any issue in understanding things. So right. So that is your Hamiltonian, and then what is being asked. So suppose if the state of system is uh, given this way. I mean, so this is your I mean the generic way to write your uh, quantum system. You I mean you define your state in Schrodinger equation and you evolve it. But it is given that like your psi is defined like this. So I mean, you can say that psi is the solution for this Schrodinger equation, which is this, where H naught is the time independent part of free Hamiltonian. So yeah, and then determine chi with the help of interacting Hamiltonian. So what is interacting Hamiltonian? So like we'll see. Some we have to like determine this guy with the help of HI. So uh, and assume the initial state of chi to be some upstate. So here what happens like uh, one of the important thing of this, I mean, yeah, one of the important thing about right, so one of the important thing when you are dealing with time dependent Hamiltonian, so you need to know like this is not as trivial as like time independent Hamiltonian. So when you're trying to like evolve the system, you need to go to a different like formalism. Like we adapt a different picture which we call interactive picture. So like how that works. So you can see here. I mean, in this Hamiltonian that we just walked out right here. So here, like the Hamiltonian, like it is something of this form, this h of t. Like I can break down this Hamiltonian, something like this e1. Uh, yeah, something e1 0 0 e1. This is e2. So plus some vector k minus I omega t v I omega t 0. So that is what like where e1 is equals to minus gamma b naught h bar by 2 cos theta, and your e1 is negative of e2, or basically e2 is negative of e1. Then you have k, that is equals to minus gamma b naught h bar over 2 sin theta. So this is uh, your Hamiltonian. So like why I'm separating this to let you know that this Hamiltonian something attains this kind of structure. Let me call this is something HP. This is the bottom part of the Hamiltonian. So so here you will see that with a H naught, this is your free Hamiltonian, uh, or like this is a time independent part, time independent Hamiltonian, which is called free Hamiltonian, and this is your time dependent part of Hamiltonian, like which is like perturbation or perturbed Hamiltonian. So like in question it was given that the psi t, like uh, it was something like evolved uh, as something minus I s0 over h power t chi. So this h0, that is your free Hamiltonian. So, like what happens, like for example, when we were normally studying so far in this quantum mechanics, about the evolution of a state, like how we used to do. Like earlier, we used to have some time independent Hamiltonian, something h. So, and using this h, like if we want to evolve a system, let's say some system like psi, which was given something as psi c1. Uh, let's say something size even the initial state is something c1 psi or c1 phi 0 or phi 1 plus c2 phi 2. Then if we want to evoke this, what we used to do, like we used to make psi at t equal to t, we used to operate this minus I h over h bar t psi 0. So this is this is something which is very fine, and this is allowed, like when you are dealing with time independent, uh, when you are dealing with time independent Hamiltonians, because this is the main thing, like right here, the evolution operator. So this u of t, like how we used to write, so that is something written like this exponential, uh, like minus I over h bar h, uh, t prime you integrate with dt. So since when you have h of t prime to be something h naught, time independent, then you can easily write exponential minus I h bar h naught t. So this is what I mean. Uh, you can write free Hamilton. So you can, uh, yeah. So the evolution operator was very trivial and straightforward. But now, when you have time dependent, this h of t, first you need to like integrate it. It's not just integration. There are more to it. Like you will have to do time ordering. So I think that would have been like told to you in this course, like, or perhaps it would be like there in some upcoming session. But I think this is something we should have been told you. So something we do time ordering. So like we write exponential in this entire thing. So yeah. So this time ordering, like we like uh, break the time into intervals of in a sequence and then integrate it. So that is what we have to do when we are like looking at time dependent Hamilton. But for time independent Hamilton, it's just simply uh, this thing will act as your evolution operator. So that is what we have to think. So in order to like avoid this, there is a way to solve this problem. So like uh, like we really do not have to like look into this one. I mean, evolution operator, like without estimating this, we can also do that is in the interaction picture. So that for that we have to first create an interacting Hamilton. So like so how can we do that? Like for example, I mean, so yeah, in so let me write like like we have h is something h naught plus some time dependent part. H naught is the time independent part. So then like in yeah. So if I write the Schrodinger equation, then I have del psi h naught plus hp psi. Okay. Then now if psi is given as something, psi of t is given as something exponential of minus I by h bar h naught t chi of t, then using that in Schrodinger equation. So plus h naught plus hp. So this is equals to, yeah. So from here, like you will get uh, h naught and yeah, exponential minus I by h bar h naught t, then chi, then further you will have plus I h bar IH bar minus IH bar H naught T. So I'm just simply taking the derivative according to the normal product rule, then that is equals to your RHS, which is H naught plus HP T minus I into H bar H naught T chi. So you can see like this first term and this thing will cancel out. So I can cancel this and this part. So then you are left with only this I H bar minus I H bar H naught T del of chi del T, that is equals to HP of T minus I H bar H naught T chi. Then I can write IH bar del chi del T, that is equals to uh, exponential I H bar H naught T HP T H bar H naught T chi. So what I did, like I multiplied IH bar H naught T from left in LHS and as well RHS. So 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 like why I'm doing this? Because these are this exponential. Like I cannot just drag them out like normally how we do, because right now this exponential, so like inside this exponential you have this h naught, which is a matrix or which is an operator. So when you have operator, you remember like you cannot just simply, like if A is some matrix and B is some matrix, you cannot just do a plus b, or like if in LHS you have e to the power a and some h, and then you have something hp e to the power a, then you cannot just simply cancel them out. So like that is the I mean the rule. Like I mean these are not just normal exponentials. So you have matrices in them. So you have to like there are rules to compute those kind of things using DCS rule. I think again something similar we discussed last time around. So like this exponential when you multiply from left. So in LHS you have this thing I h bar h naught t and I h bar minus I h bar h naught t. Since you see like here this thing I can write to be e to the power z. Why? Because if I have something e to the power a, e to the power minus a, even though it is like some matrix, but same a is there, then I can write it e to the power 0, because like uh, the rule is like if you have two things e to the power a and e to the power b, you can you cannot write e to the power a plus b if a commutator with b is not 0. But if you can write e to the power a e to the power b equals to e to the power a plus b if a and b commutes. So same here also, like this I can write it as uh, e to the power 0, because a commutes with itself, that is a commutator with a is 0. So that is why I can write that. So when I'm multiplying e to the power I h per h naught t from left, so in LHS you will have this term, so which will effectively become e to the power 0, that is one. But in RHS, so this will happen. So again, when you're multiplying from the left side, this you will have and 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 from right side you already had this exponential factor, so in the middle you have HP. So now like what this will become finally. So I can write I h bar del chi del t equals to hi. So this is the interacting Hamiltonian which I was talking about. So hi t is the interacting Hamiltonian. H naught t hb t minus I h bar h naught t. So right here. So using this Hamiltonian, we have to uh, like uh, like like understand. I mean, we have to calculate this chi. So in the question which we were looking into, so that is what we have to determine chi with the help of interacting Hamiltonian Hi. So then yeah, we have to find it what is chi of t, and chi of t equal to 0 is given to be upstate. So this is spin offset of SZ. Let me, so this is SZ upstate. So okay, and so here we can like show you how to do so step. Yeah. So now first of all let me calculate what is this exponential of minus I h bar h naught t. So this is h naught is your matrix which I showed you. It is e1 0 minus e1. So that I can write it as uh, exponential of minus I, uh, or like I can show you how can written without showing you directly. So you basically you have to what expand this exponential series. So I hope you are aware how we expand this exponential series. So first you will have identity operator, then uh, uh, minus I h bar h naught uh, t, then 1 by 2 factorial minus I by h bar h naught t whole square, and so on. You will have this like this is normal e to the power a expansion 1 plus a plus a square by 2 factorial, like that. So first term we have just simply identity matrix, then we have uh, a1 h bar t, and h naught, as I was telling you, if it was something uh, e1 0 0 minus e1, then 1 per yeah 1 by 2 minus I h bar t square and h naught square, that is c1 minus c1 square, and so you will have this. That means I can write it as sigma power n 1 by n factorial minus I t over h bar to the power n e1 0 0 minus e1 to the power n. So like you I mean I think you should know that like when you have a diagonal matrix, when you are trying to power them up, so you just simply power the diagonal matrix of that matrix. That will be the matrix of that will be the power of that matrix effectively. So like if I have a matrix is 1 0 2, then a square is simply 1 0 0 4. So yeah, that is how like you can uh, tell here as well. Like when I'm writing e1 0 0 minus e1 to the power n. So like if n is 1, then it is simply first order second. If n equals to 2, then that matrix will be e1 square 0 0 e1 square. Both the entries will be e1 square, and if it is cube, then e1 cube 0 0 minus e1 cube. So that is how you get it, right. So, so finally, your so this again forms a exponential series. So this is a like I mean overall factor. So this is an overall factor. Like you can multiply that and you can get e1 0 0. Yeah. So that is what you will get. So we have like we'll be using this exponential, I mean this matrix exponential form. So that's why it's better to calculate it before. And so now like what we are supposed to calculate, that let's say that chi, the quantity which we have determined in interacting presence of interacting Hamiltonian, C1, let's say it is something C1 and C2. And so this like when you evolve this with free Hamiltonian, like you evolve this with, so H naught is the free Hamiltonian, remember it. And so you get something psi, let's say call it D1 and D2. So so that means like you can calculate what is D1 and D2 using this H bar H naught D, C1 and C2, because psi is given to me H naught D chi. So so that means I can write B1 B2 equals to uh, exponential minus I, yeah, I over H bar B1 D 0 0. This will be plus sign. I wrote it minus before. So then I H bar B1 D C1 C2. So that means you have uh, D1 is C1 minus I H bar E1 D, and E2 is C2 E to the power I, and this will be plus E1 D. So, right. So this is your D1 D2. So like I think this was not asked in the question, but this is like another part of that question, like what you can edit, like what will be your psi. So the psi is basically this, and so after all you have to find what is C1 and C2, because that is what the question it is asked. So like for C1 and C2, we have to go to the interacting picture. So as I was telling you, like we have to calculate d of chi by dt equal to h and chi. That is, I mean, you have to calculate uh, this one right here. So, for that we need interacting Hamiltonian. So you're getting this part or any problem in any understanding, any issue you can.
Yes, not too much, but it's
Uh,
okay. I will read it through.
okay, okay. So like where exactly you are having problem?
My question is the
Uh,
calculation is okay,
uh,
but I have one question.
uh,
So when you are calculating the interaction, the problem in the interaction picture,
yeah, yeah.
before
Uh,
at the time evaluation, it should be why you put there is not free
uh,
Hamiltonian. It should be the full Hamiltonian. Why not the full Hamiltonian? Or
like so you're talking about uh, this thing.
uh,
You're talking about this thing.
yes, yes, yes.
Yeah, so this is what like
Because
I mean it is given in the question that the psi of t is evolved with h naught because this like what you do. I mean as I like said you like let's think about like for the case when we have time independent Hamiltonian. Like we do not have any time dependent term inside the Hamiltonian. What we do simply we write psi of t uh, minus I h naught t psi. That is what we write because
yes,
like for time independent Hamilton, h naught is the time independent Hamilton. That is what we write. That is a full Hamilton when you are dealing with time independent Hamilton. But when you have time dependent, like we are like separating this Hamilton into a time independent part and time dependent part. The time dependent part we are calling it as perturbation. So uh, there what happens we have.
no, no, no. But,
Hmm, hmm,
I think it is okay
uh,
because you are talking about the time independent free Hamiltonian,
uh,
and then you are adding some perturbation that is HP.
yeah, HP, right. So that is the time dependent part, which is making your total Hamiltonian to be time dependent.
Okay.
So now in time dependent, so like I mean my notebook is like I mean it's bit
So
lagging, so
my
I'm closing
my
it and
question is that
yeah, yeah, you can go on.
my question is that
Uh,
initially you can break the Hamiltonian into two part, say time independent part and time dependent part.
right.
So for the time dependent part, you are showing time independent part. You are showing the Hamiltonian evolves with the free Hamiltonian.
For time independent part,
Time independent.
mhm,
It evolves with the free Hamiltonian. But say consider the full system. The wave
mhm,
function of the system evolves with the part
full
with the
Hamiltonian.
full Hamiltonian.
Right, right. Yeah, that is what I'm telling. So like,
Okay.
uh, look, I mean when we have the system, let's say we have some Hamiltonian which is completely time independent, H naught, like for time independent Hamiltonian, time independent Hamiltonian. So then you evolve your system psi t equals to I H naught t. I am not writing H bar, you can consider it to be 1. So that is how we write for a time independent Hamiltonian. Simply we write this exponential operator because this u, that is your evolution operator, u of t, that is written as exponential of minus I h bar. So there will be h bar h naught dt. So you can just simply, since h naught is time independent, so this will just simply be h naught t exponential. But if I have right now, if I have some time dependent Hamiltonian, let's say some, and I'm writing the time dependent Hamiltonian, let's say this is time dependent Hamiltonian. then uh, psi of t, I have to write, I cannot write the psi of t as I h bar t psi of 0. Like, why I cannot write this? Like, can you say this? Like, why this is not allowed? This psi of t.
Actually, I don't know.
So,
I don't know.
like you cannot write this psi of t when your h is time dependent, because this evolution operator u of t uh, is not equals to I h by h bar t. It is only equal to if your h is time independent. But when your h is time dependent, you cannot. When your h is time independent, you can write your evolution operator as this. But when your h is time dependent, you cannot write your evolution operator something as minus I h bar h naught t or h t. That is incorrect, because you have to how this evolution operator comes. This comes from here. So when you have time dependent Hamiltonian, you will write your u of t as something exponential minus I h bar integration h of t dt. First you have to integrate this h with respect to time, then you will get some exponential something, then that you will and also with that there is a time ordering. Like if I time ordering means like that is the order of integration. Like that is the, you break the time into intervals and you integrate them by this, like in a sequence of order. Like if your time runs from t0, t1, t2, t3, so you break into intervals. You will first integrate from t0 to t1 and t1 to t2. That is what time ordering means. So I'm not going into that detail, but I'm telling you what you in when you have time dependent Hamiltonian, your evolution operator will be this, like exponential of the integration of h of t dt. And after when you integrate, then that will be your evolution operator, and then you can use that u of t. You can use that u of t to write this u of t psi 0. But when you have time independent, you can just simply write psi of t equal to u of t psi 0, where u of t is your time independent Hamiltonian. But that you cannot write uh, here. I mean, you have to use this u of t.
Okay, thank you. Because it was my problem actually at this point, but now it is clear.
Uh,
So I will get this topic in the Heisenberg picture
yeah, yeah,
discussion.
Heisenberg picture.
Okay, okay,
Uh,
okay, okay. I
so
have to read it. Okay, okay.
yeah, yeah,
But now I'm okay. Okay,
uh,
thank you.
yeah. So that is why you cannot use the I mean the free Hamiltonian like when you are in time dependent. But again, like I think your question was something why I'm not using the full Hamiltonian. Like
Yes.
that is what you were asking. Like I said, like let me like erase this part. I think that is okay. Or maybe I just yeah. I think erase the part. So uh, and further you were telling. Uh, we are writing psi of t is something like this, and why we have only x0 right here. So this is what you were telling, no? Like why we are having h0 and why it is
Yes.
not full Hamiltonian, because the the hp part, the hp, it is already captured in the state chi. The chi of t, it is already captured in the hp part is already captured in the chi. How, like as we were telling right now, this chi of p, like because you see this chi, it is determined from this equation. Chi is determined from this equation. Like if you solve this Schrodinger equation, you will get something chi of t. Like this is the solution. Solution you will get chi of t. And this chi of t, how this chi of t is obtained, like solving this Schrodinger equation, and in this Schrodinger equation you have Hi interacting Hamilton, and this Hi contains your bottom part, and that is like the that is how it is defined. You sandwich this bottom part between these two exponentials. So
Okay.
in Hi you have the perturbation part. So that's why like this chi of t, the solution you will get, it will already have the uh, it will already have the effect of evolution. Like you are like let's say you are going chi 0 to chi t, then then this will go through some Hamiltonian. That Hamiltonian is Hi, and Hi contains this Hp part. So this guy already has the your question was like your guy already has the Hp part. I mean the contribution of evolution which will come through this Hp part is already encoded in this chi of t. And now we are writing the psi of t, like which is only evolved from S0. So is this clear, or any problem, like still not clear, like I can.
No. Okay. Okay. It's okay.
So yeah, that is what, like we have to now determine what is chi. We have to determine chi from Hint. So so for that first we have to calculate what is Hint. So Hint we can calculate, as I just showed you the definition right before. I can write Hint as exponential minus I h bar h naught d hp. That is the time dependent part or the perturbation, I h bar h naught d. So yeah, and I min e to the power minus I h bar h naught t is this, like as we just computed right here. So using this, I can have the total agent form. So that is, I can write it as k 0. Um, yeah, k 0. Sorry, this is not. So we have this one, e to the power minus I h bar h naught t, and for e to the power plus I h bar h naught t, then the sign will be changed. Here you will have plus and here you will minus, and then hp, our hp is this, like earlier I just showed you. Your Let me write this hp here. Hp is k 0 minus I omega t I omega t 0. This comes from here. This is here. So this is your H naught, and this is your HP. So and that HP is written like this. That is what we will use to calculate the interacting Hamiltonian. So yeah, so I have K, then exponential minus I h bar E1t 0 0, then exponential k h bar E1t, then 0 exponential minus I omega t, so t 0, then exponential I h bar e1 t 0, exponential I h bar e1 t minus I, yeah. So then that I can write it as uh, yeah uh, k uh, okay. So first I have to multiply these two matrices. Then that will give me like 0 minus I h bar e1 uh, minus omega t. Then right and 0. So this one is 0. This is exponential I by h bar e1 plus omega. So this is minus is this plus omega t 0. Then exponential I h bar e1 t 0 I h bar e1 t. So this will give you k 0 and so yeah 2e1 plus omega t, and here you have I h bar uh, 2e1 plus omega. I think there is problem somewhere. Okay, yeah. Omega t 0. Actually, like here I'm using like okay, for now let me use h naught as something e1 0 0 e2. Like this is e2 minus e2 is minus of e1. Like I can like substitute at the end, but if I just keep it what is e1 and e2, so that will be uh, good to know the actual form, the general form. So so if there is a sign problem that I have messed up somewhere, so that's why I can like this metric is easy to compute, so you can just simply multiply it. So I was having some sign issue, so I have changed the I mean minus e1 to e2 because like to get the general form. So then at the end you can substitute. So here k I can like I'm directly like I can write the form. So just you multiply these three matrices and then you will get something this 0 I by h bar e2 minus e1 minus I omega t. Then you will get e minus I omega naught minus sorry. Okay, so yeah, then you have minus I h bar e2 minus e1 Here you t, t plus I omega t 0. Then now let me write e2 minus e1 as some omega naught h. And so like right, e2 minus e1 as some omega naught h, and omega naught h is gamma b naught h for cos theta. So that means I can write h I as k 0 e omega naught minus omega t e minus I omega naught minus omega t 0. So like uh, so I haven't done like something uh, like very serious here. Like it's just simply I have multiplied these three matrices, and like earlier which I was using this E1 and E2 to be minus E1. So right now I'm just keeping it everything as E2. So in this evolution operator matrices, this matrix exponential. So then just you multiply, and then I'm just doing this. I'm calling this E2 minus E1 to be omega naught h, and and this omega naught, like as I earlier showed you, what is E1? I told you E1 is something. Uh, what was that before? Right here, E1 is this thing minus gamma b naught h bar by 2 cos theta. So h bar by 2 cos theta. So that means if I am calling like if you minus gamma b naught cos theta by 2 h naught, this is your omega naught. No, I mean twice of it will be omega naught. This is omega naught by 2, and e2 is minus e1. So this is just notation, like I'm just like for I'm keeping it as general, so don't get confused with it. So just forget about like uh, what is into and D1. Like just try to see like how we can come to this edge interaction. So this is how you would write the edge interaction. You multiply these three matrices, and once you get this edge interaction, now we can put it in the Schrodinger equation. So this is like we call it as uh, the interacting picture of Schrodinger equation, and then from here we will calculate then uh, I mean what is chi of t. So and chi of 0 is also given, that is the upstate. So uh, yeah, okay,
No.
yeah,
So in actually it is okay.
okay.
So in the interaction matrix,
Mm.
this omega naught is mainly coming from the free Hamiltonian, and this omega is
Right,
coming from the part of it.
right,
So
yeah.
everything is embedded in the interaction picture.
Yeah. So, of course, yeah.
So,
That is exactly you, you figured it out very correctly. So that is how you can interpret it. So that omega naught actually comes from your free part of your Hamiltonian, the intrinsic frequency, or like the intrinsic part of the Hamiltonian, and omega comes due to the strength of time dependent like perturbation you are providing. I mean, that comes from the strength of the perturbing field. So, right, that is how you can interpret, because our Hamiltonian was like this. So, this e to the power minus I omega t, like this is your part of the perturbation. Omega here, omega is there, and omega naught, like from E1, I was calling omega naught. So I was calling E1 is something omega naught by 2 h. So E1 contains the omega naught, and this second term has this omega. So that is a quarter vessel, right? So yeah. So then, uh, okay. uh, I have the interaction Hamilton right now. I have to like figure out what is chi by putting them in the Schrodinger equation in the interaction picture. So that means I have to let me write this. This is what I have to do. Hi chi. Uh, that means I h bar d by dt. I initially called chi to be something C1 of t and C2. So C1 of t, C2 of t equals to uh, let me get the Hamiltonian interacting Hamiltonian, that is zero C1 of d C2 of d. So then you take dc1 dt, that will give you k I omega naught minus omega dc1, and similarly we will have another differential equation, that is dc2 k minus I omega naught minus omega d c2. Sorry, this will be C2. This will be C1. Yeah. So this is the like differential equation you get when you solve this. So now you see that both this differential equation they are coupled differential equation. So I hope you are aware of coupled differential equation, or
Yes, yes.
you are
Okay.
aware of coupled differential equation, right?
Yes.
Okay, yeah. So this is your coupled differential equation because you are you're having a derivative of C2, and in that expression you have C1. C1 derivative is with C2. So I mean, so in order to solve what is C1 and C2, you have to first decouple them. You have to separate the differential equation only in C, where you will find C1 term along with its derivative dc1 by dt. Same way, you just write what is uh, differential equation only in C2. So to decouple them, like we just do a very smart trick. We take the derivative on both the equations once again. So let me write uh, what was k initially. We're taking so k is this minus gamma v naught h bar by d. Okay, so okay, let me just okay. Like just for now, let me just write it dc1 by dt as something z. So g is the k by I h bar. So I minus omega dc2 dc2 by dt as uh, or let me write minus r2. So g is like k by h bar, here also minus I z minus I omega naught minus omega t c1. So like to decouple this two equation, I have to take derivative once again. So d square c1 dt square. So in LHS, in RHS also you will take that derivative, that is you apply the product rule, that is you will get uh, I omega naught minus omega d c2, uh, then plus omega naught minus omega d dc2 dt. Same way you take the derivative of the second differential equation. Even there, like you will have same similar type of expression. So or let me just write the first differential equation itself. So z of omega naught minus omega e to power I omega minus omega naught t c2 minus I c e to the power I omega naught minus omega dc2 dt. Now, like we have to convert this d square c1 dt square, that differential equation, only in terms of c1 variables. So now you can see c2 is hanging around here in this second order derivative differential equation of c1. So then I can substitute what is dc2 from here. So now if I do that, and also uh, I can substitute what is C2 from this uh, expression, from this differential equation. So so like DC, yeah. So, then C2, I have C2 as, so K by H bar I'm writing as Z. So if I take it to the left hand side, that will be 1 by Z e to the power minus I. So this will this will become, so Z will cancel out. So I'm substituting what is C2. So you substitute what is C2 and DC2, DC2 by dt. From there you will get like the okay. So this DC1 dt plus uh, Z is this. So here I is DC2. So G square exponential minus, okay, that means we have plus uh, plus minus c square c1. So that means you have differential equation is I omega minus omega, and the first term is plus. So this will be minus plus c square c1 equals to 0. So that is your differential equation, only c1. So same way you can do it for DC2 as well. So that, like you can C. So for C2 you will have d squared C2 d squared C2, that is that is dC2 d2 plus C squared C2 equals to 0. So these are the two differential equations. Only in C1 and C2 variables you get it, and now if you would see, like if you want to solve what is C1 and C2, let's say like if you solve for C2, now this differential equation is easy to see how can you solve it. So C2, like I can, like this is a second order differential equation. I hope like you are aware of what is the solution for this linear or ordinary differential equation. So these are not very difficult differential equation to solve. So this is just simply a second order linear uh, ordinary differential equation. So here you will get C2 as the general form of C2 is something given as uh, some constant a plus e to the power I alpha plus t plus a minus or minus I alpha minus t. What is alpha plus and minus? So that is alpha plus and minus is given as minus omega of minus omega plus or minus omega minus omega square plus 4c square over 2. So like you get this differential equation, you get the solution of this differential equation first by like you change the differential equation into some kind of auxiliary equation, and then you solve the roots for that auxiliary equation. That roots are basically given by alpha plus minus, and so that is what when you write in terms of exponential of I alpha plus and exponential of I alpha minus, that would be a solution. Along with you will have two arbitrary constant which you calculated by initial conditions. So same way we also have initial condition here. So now yeah, then so you got C2. Likewise, you can calculate what is. Um, so let me just tell you how you get this. You just basically calculate this one. So from here you can get what is alpha plus minus, and then C1 is basically so here I can get this is C2 C1. So C1 I can calculate it that I can just simply put here in this expression. The because here I don't have to solve any differential equation. I know what is C2. Just I take the derivative of C2 and I get what is C1. So from that, like I get C1 uh, will be something 1 by Z I omega naught minus omega t dc 2 by dt. So right then uh, C2. Just could you hold for a minute? Uh, Hello. Uh, अभी एक्चुअली थोड़ा टीए चल रहा था तो मतलब देख आपको मैं अभी आधे घंटे में चेक करके बताऊँ. Okay. So yeah, sorry for that. So yeah, I was telling like you can calculate what is like C1 from here. So yeah, you will have C1 from you have C1 and C2. So that is what you got it. Like I mean, after all, that is what you needed to calculate. Now just C1. I mean, one more thing. What is the value of A plus and A minus that you have to calculate from initial condition? So like now the initial condition, let me properly again. What is C2 is 1 by Z uh, e to the power. Uh, yeah, okay. This is C omega naught minus omega t. So I have I a plus alpha plus e to the power I alpha plus t then minus I a minus alpha minus e to the power I alpha minus t. So I got so this is C1 and we have also C2. Now this initial condition for initial condition is given C1 at t equal to 0 is 1 and C2 at t equal to 0 is 0. Why this is so? Because in like if you see like in the question it was given assume the initial state that chi of 0 is something this. So for sz spin that means for uh, for sz like you write this as 1 0. So we know what is C1 and C2 from here. Like you will get like what is uh, A plus and A minus. So so C1 of like from this you will get uh, so you put uh, t equals to 0, then you have A plus alpha plus uh, then minus A minus alpha minus by z equals to 1. So that means A plus alpha plus minus A minus alpha minus equals to z. And further, you from this you will get uh, A plus A minus equals to 0. So if you solve these two equation, let's say this is C and this is something, let's call it like this. Uh, yeah, so, yeah, something. Uh, 1, 2. So from 1 and 2, you get A plus equals to Z alpha minus alpha plus and A minus is minus of A plus. So so that is what you get. So you got A plus A minus. So then you finally have C1 of T. So you put what is A plus like so this is your C1, right? And similarly, you have C2. So this is C2. So you got a plus and a minus, you substitute them and you will get what is C1 of t and C2 of t. So that is what you need to calculate. So you got chi of t, what is C1 of t and C2 of t. So yeah, that is one. So like, did you get this? Like, I know this is a very rigorous like mathematics. You need to go to find out what is chi of t, but this is how you calculate it using interaction picture. Like you first calculate the interacting Hamiltonian and you put it in Schrodinger equation. That's it. Like, then the
Yes.
technique is same. Like
I
how we
think the
did it for
concept,
yeah.
I think the concept is important. Although the calculation is lengthy, but it's okay.
Okay, so
You can
did
make
you
it
like
effective.
get the part on how we are doing
Yes.
this? Like
Can you give a diagram, say in short, from
uh,
the beginning of this problem to last?
okay,
The
so
process, the whole
okay,
process
okay,
in
okay,
some lines.
okay,
Just the important part.
okay, right, fine. Awesome. So, like what we did, like in the question, it was given, like initially, like you get the like first question, how we calculate that.
Yes, yes,
So yeah, like how we calculate for first question, the same we also did here. In the first question also, we calculated this chi of t, uh, this chi of t. So,
yes,
but that chi of t we directly calculated without using any interaction picture. We do not have
yes.
interaction. We just simply put that uh, in this Hamiltonian. So yeah, so in this Hamiltonian we got it. But here first you need to calculate using interaction picture. So that means you first need to calculate what is interacting Hamiltonian. So if to calculate what is chi of t, to calculate what is chi of t, you first have to put you have to uh, calculate this hi. So this HI is calculated using what is your total Hamiltonian. So I mean not total Hamilton. You first break your total Hamilton into H naught and HP, and from this HP you basically calculate what is HI. That is exponential of minus I H0 to H bar HP and I H0 by H bar T. So that is how you calculate HI. And once you calculate HI, then the process is same. Same process like how we did in the first question. You put them in the you put them in this Schrodinger equation. Then instead of H, there will be HI in the second question, which we did. And then you solve it. Like you get two differential equation. Then you decouple them. After decoupling, you solve what is C1 and C2. Uh, I mean, like how we followed for first question, the same thing we also have to do for the second question. Only we have to just
Is it?
additional thing we have to compute is interacting Hamilton, because from that you will put that in Schrodinger equation and you will solve. There
Okay.
is no big difference between first and second question. Only one thing is came here is like what is this what I mean this interacting Hamilton. Anything more like or
No, it's
fine. Okay, so